Good morning, everyone. We'll get started here today with this last section in Chapter 5 that we're covering for Midterm 2 next week. We were briefly getting into enthalpies of formation. I'll come back to the slide we were on last time after this slide here. What I wanted to mention is that we define formation enthalpies, the enthalpy it takes to form a substance from its elements in whatever their most stable state is at room temperature. And so for a lot of substances that we use a lot, like H2, O2, N2, F2, those are the most stable forms of those elements. So if you imagine the formation reaction of O2 gas, so the formation reaction for O2 would just come straight from the same substance, O2 gas. So the delta H of a substance forming itself has to be delta H of 0. So these are defined to have a delta HF exactly at 0 because they would be what you call an identity reaction. Just the substance being formed from itself. There's no enthalpy change for that reaction. And so the substances that are defined to have a 0 delta HF are things like H2, N2, O2, F2, Cl2, all the noble gases, so helium, neon, argon, krypton, those atomic gases. And so those are our gaseous elements. We have two liquid elements, Br2 liquid, mercury liquid. So if we had, what is the delta HF of Br2 liquid? Well, that's the most stable form of bromine at room temperature. So this would be coming also from this same reaction. So that delta HF would have to be exactly equal to 0. So a formation enthalpy is form a substance from its elements in their standard state. So if you're forming an element where it's already in its standard state, that enthalpy has to be 0. There's a lot of solid elements. We have all the other metals other than mercury. So we have our metallic elements, so that would be sodium metal, calcium metal, iron metal, etc. We have a couple common ones, like carbon graphite is the solid form of carbon that has a 0 delta HF. Carbon also has an allotrope of diamond, which has a slightly different enthalpy of formation. It's not exactly 0, but it's graphite. That's the most stable form of carbon. White phosphorus, sulfur, rhombic. I don't think I'd expect you to memorize white phosphorus versus rhombic sulfur, but just to kind of show you for phosphorus and sulfur what their most stable forms are. I2 is a diatomic molecule like the other halogens, but it's a solid. So the delta HF of I2 solid would be 0. So the implication would be that if you had other forms of these elements other than these standard forms, that they would have non-zero delta HF values, and they would not be defined to be precisely 0. So hydrogen would not have a delta HF of 0, just H2 would. So hydrogen atom would not be defined to have a delta HF of 0. Oxygen atom would not be defined to have a delta HF of 0. We'll talk about bond strengths when we get back after midterm 2, but if you think about a bond strength, every bond that you have formed requires energy to break. So that means that H2 gas converting into two H atoms, that the delta H of this reaction has to be endothermic. Heat has to be absorbed to break that chemical bond. And that's going to be true. We'll see this more in section 5.8 after midterm 2, but any bond that forms requires energy to break that bond. And so the H atom, therefore, has to have a positive enthalpy of formation. And certainly is not going to be 0. And so carbon diamond, a different form of carbon, has a non-zero delta HF. Another form of phosphorus also would have a non-zero delta HF. Sodium gas. If you think about the solid to liquid to gas transformation of any substance, this comes up a little bit later too, but solid to liquid to gas, we can sort of predict that any substance has to absorb heat to melt. So we have to increase temperature, increase heat. So this process here is always going to be endothermic. Also, you have to absorb heat to boil, so it's always endothermic to go liquid to gas. And then if you flip those reactions, of course, they go exothermic. So if you want to go gas back to liquid, that's exothermic. Delta H is less than 0. If you're freezing a substance, heat is given off by that process, so delta H is exothermic for that process. So we can just make sure that we have for phase changes the idea of going forward versus backwards. And so if you imagine sodium solid delta HF is 0, the delta HF of the liquid has to be higher, the gas even higher in order to form those substances. Certainly not defined to be 0. So you gotta be a little careful. If you see an element, it's not necessarily 0 unless it's in its most stable form, where it's solid for most of our metals except mercury. For most of the nonmetals, it's gas, but we do have Br2, nonmetal, that's a liquid. I2, that's a solid. Carbon, sulfur, phosphorus, some common examples of nonmetallic elements that are also solid at room temperature. Okay, so then let's kind of then remind ourselves of how we write formation reactions. So a formation reaction is you form the compound from its elements in their standard states. So we take the carbon and CO2, has to be in the form of carbon graphite, oxygen in the form of O2 because those are the most stable forms of carbon and oxygen. When they react together to form CO2, that reaction's enthalpy is defined to be the delta HF of CO2. So if you think about the products minus the reactant's enthalpies, if we're saying that this delta HF is minus 393.5, these delta HFs are 0. So the delta H of that reaction would be equal to minus 393 kJs. So we're going to see the utility of delta HFs is you can take the sum of the products minus the sum of the reactants. And if you have a formation reactants, if you have a formation reaction, the reactants all sum to 0. That's the idea of the formation reaction, is that all the reactants, sums of their heats of formation sum up to 0, and then the delta H of that reaction just corresponds to the enthalpy of formation of the compound. So we always write a formation reaction to form 1 mole of a compound. So a formation reaction would form just 1 mole of water and actually just leave the O2, if it needs to be a fraction, just leave it as a fraction. So the proper formation reaction for water gas is being formed from H2 gas to give us the hydrogen and half a mole of O2. And this is the one reaction we can actually leave legally balanced, if you will, with a fractional set of coefficients. So the meaning here is you take a mole of hydrogen, half a mole of oxygen, combine those to form a mole of water, and the enthalpy associated with that reaction is minus 241.82 kJs. That's kJs per that 1 mole of water. So we define that to be the delta HF of gaseous water. You can determine the delta HF or look up the delta HF of liquid water. We're going to see that these delta HF values, there's a big table in the back of the textbook that lists these for a variety of substances. Because they have a lot of utility, we're going to be able to use these delta HFs to calculate delta H's of reaction. That's going to be the main idea here, is we want to be able to look these up to take the sum of the products minus the sum of the reactants. And so for water liquid, just notice that it's a different value. So physical state matters, so you have to match the physical state to the proper state. So the delta HF of liquid water, slightly more negative than the gaseous water. Another way of thinking of it is the gaseous water is higher in enthalpy. It's less negative, right? So if you go from liquid water to gaseous water, that's uphill in enthalpy. That means liquid water has to absorb enthalpy, which we were just talking about on the previous slide. And so we can write these formation reactions. Again, if you're forming O2 gas, the formation reaction is just straight from O2 gas. The delta HF is therefore defined to precisely be 0. We could write the formation reaction for some other form. We call it an allotrope. Not a very big term necessarily to remember, but allotropes are just different forms of the same element. So an important allotrope of oxygen is ozone. The formation reaction would just come from O2 gas, and then balancing this out with the fraction 3/2 O2, balances out to 3 total O's on both sides of that reaction. And then you see here that ozone has a positive delta HF, certainly not 0 is the idea. So definitely a non-zero delta HF, not defined to be 0 like O2 is. So this is very much kind of a definition or defined off the system on how we're using and defining enthalpies of formation. For CH4, we would just write this from carbon solid graphite. Sometimes we just write this as just carbon solid, and it's understood it's in the graphite form, but then plus 2H2 in the gaseous state. That reaction there corresponds to the formation reaction of CH4. So there's kind of 2 flavors of questions you're going to see on this section. One is just writing the formation reaction for a given substance, where if you're told to write the formation reaction for, I don't know, like let's just say ethanol. So if we're writing the formation reaction for, that's not ethanol, it would be C2H5 hydroxyl. So if you want to write the formation reaction to C2H5 with the OH group, then we're just writing 2 carbon solids, graphite, plus 3 H2s in the gaseous state, plus 1/2 a mole of O2 gas. That corresponds to the formation reaction of ethanol. So if you're ever asked to write the formation reaction for a given compound, it's always from its elements, but it's elements in their standard state. It's not like 2C gas plus 6H gas plus O gas. It's specifically H2 gas because that's the elemental form. That's the most stable form of hydrogen. O2 is the most stable form of oxygen. And then carbon graphite's the most stable form of carbon. And so then the utility of these, the second question we tend to ask is then, well, let's put them into use. Let's put these into practice to solve for delta H of a given reaction. And so we see here tabulated and written out the full formation reactions of a couple different molecules from the previous slide, like the CO2, water, gas, water, liquid, CH4 gas. And we're asked to determine the delta H for CH4 gas forms, reacting with 2 O2 to form CO2 plus 2 waters. The delta H of this reaction would be calculated by taking the sum of the products delta HFs. So just like a delta, take the sum of the final state, the products, and subtract the reactants. If you recall, we kind of got into this topic by saying if we could just tabulate all the absolute enthalpies of these substances, we would do that, but they're tricky to measure. In the lab, we're almost always determining a change in energy from one substance to another. So it's much easier to study reactions in the form of like calorimetry, where you're calculating reaction differences in enthalpies. So we tabulate these values in tables, these delta HFs, and use them like their absolute enthalpies. Just the idea, the enthalpy of the products minus the enthalpy of the reactants. We just have to account for stoichiometry. So I just want to take 1 mole, if I'm working this out here, 1 mole times the delta HF of CO2 plus 2 moles for water, because I have 2 here, 2 moles times the delta HF, but specifically water gas. I need to subtract 1 mole times the delta HF of CH4. Of course, CO2 has to be a gas, but that's the only one in the chart. So we just make sure that we grab the water gas and not the water liquid value. We don't see O2 because 2 moles times the delta HF of O2, that's understood to be 0, or hopefully understood that the delta HF of oxygen here is equal to 0. And so if I were to work this out, I would take 1 mole times minus 393.5 kJs per mole. So that gives me the number of kJs. So the mole here is canceling out with the mole unit. 2 moles, so I go plus 2 moles, because we're doing this summation. So plus 2 times 241.82. So again, the mole cancels. We're multiplying this by minus 241.82. Again, the mole cancels. And then we're subtracting, plugging in. So subtracting, so products minus the reactants. So we're subtracting 1 mole times minus 74.8. So again, the mole cancels there as well. Now, the only slightly tricky part is that we have to keep track of all those minus signs. Like I literally need to do 1 times negative 393.5, so just keep that negative sign in your calculation, plus negative 2 times negative 241.82, and then minus 1 mole times negative 74.8. So I'm just very precise in entering all those minus signs exactly where they occur in the calculation. I keep getting the wrong answer. So minus 393.5 plus 2 times negative 241.82 minus negative 74.8. There it is, minus 802. 802.3 kJs per mole. Or not kJs per mole, all the moles have canceled, so this is just units of kJs. So if you've ever noticed, or one thing to, I'll take a question 1 second. One thing for reactions is reactions are always given in units of just kJs. The moles are understood. All these moles have canceled out, and we just have units of kJs here when we're adding these up. Yeah.
Why is like the product one N and then the reactants one is M?
I think it's just trying to say, like, if you had like the products as being M times A going to N times B, so the coefficient M is just going along with whatever the reactants coefficients are, and N is just, it's just saying to account for the coefficients of the products. So this is just saying to use the coefficients in front of the reactant. So make sure to use the 1 for CO2, the 2 for water. So make sure to take account of those units, or of those coefficients. Okay, and so then using those coefficients as moles cancels out the kJs per mole. So we're doing 1 mole times CO2s, 2 moles times waters. Now, the next slide is going to show us kind of why this works out. Yes?
I think I don't know if I'm confused, or I think you put CO2 in the beginning, and I thought the CO2 was on the product side, not the reactant side.
Yeah, so we're summing up the products, all the products. So sum up the products first, so CO2 plus the water, and then subtract the CH4.
Okay, but it's not.
Yeah, so we go the CO2 plus the water minus the reactants. Now, this slide kind of shows just mathematically using Hess's law why this works. I mean, in one way you may think, well, we're just taking the sum of the products minus the reactant, so maybe it's not confusing on why it works. But the real reason, or sometimes even you may be confused on how each of these could correspond to the delta HFs as the formation reactants from their elements. If we just think of writing out the formation reaction of CO2, writing out 2 times the formation reaction of water in terms of full reactions, and then if you flip that formation reaction of CH4, because it's on the reactant side, so we need to flip its formation reaction, so we need to flip the sign on that reaction, and then notice how all the elements are canceling out. So the way that this works is that the H2s are canceling with each other, the carbon graphites are canceling, such that our net reaction is the CH4 plus the 2 O2s form CO2 and water. So it's like a Hess's law consequence that we can use heats of formation this way. So the idea is, if you have a balanced reaction, reactants going to products, the reactants are, you use their formation enthalpies, which is forming them from their elements, but then you flip the reaction. That's why it's minus reactants. And then the products, they're being formed, so we can take the delta HF of the products in the forward direction and use their delta HFs where we subtract them, we subtract off the enthalpies of the reactant. So hopefully you see that this is just a sum of those products, delta HFs, minus the sum of the reactants, delta HFs. So sum up all the enthalpies of formation of the products, subtract all of the enthalpy of formations of the reactants, and then just keep in mind that anytime you have an element in its natural and most stable state at room temperature, that it has a enthalpy of formation precisely of 0. So O2 is 0, H2 is 0, in the gaseous state N2 is 0, etc. So we just have to keep in mind the elemental form. And we're going to not try to trip you up and give you the phosphorus and the sulfur. Think of these examples giving you the O2, the H2, but not O, not H. Carbon graphite, not carbon diamond, or carbon gaseous atom. Okay, so with that kind of wraps up chapter 5 in terms of the coverage for midterm 2. We still have one section to go. We'll talk about that after midterm 2. So let's start looking at some review problems here. And so we're going to kind of go back to chapter 3, maybe get into chapter 4. If we get through those problems, we'll get into some chapter 5 problems. About halfway through this packet, it flips back to another chapter 3 to 5 kind of review. So hopefully we'll try to review a little bit out of each chapter here today. And so the first problem here says you have sodium and chlorine gas reacting to form NaCl. We're told to balance the reaction. So it would be sodium solid plus Cl2. They're going to form NaCl. The physical states aren't so important here. What's important is just the balancing, because this is going to be a stoichiometry problem of where we have 23 grams of sodium, 70.9 grams of chlorine. What's the most massive NaCl that we can have formed by this reaction? Now, what we want to do here is try to figure out which of these two reactants is the limiting reactant. So this is a limiting reactant problem where we don't know which one is the limiting reactant. So what we might want to do, since we need to figure out how much grams of sodium chloride can form, well, let's just react all the sodium. Or we can take all of the given chlorine. So let's consume all the sodium, or let's consume all the chlorine and see how much product we can get. The one that's lesser is going to be the stopping point for that reaction. So 23.0 turns out to be the molar mass of sodium. So 1 mole of sodium is 23 grams. The reaction says for every 2 moles of sodium, we get 2 moles of NaCl. 1 mole of sodium chloride is 35.45 plus 23. So that's going to be 58.5, just because it's 23 by 23 is 1, times 2 divided by 2 times 58.45. So that math there is just going to simplify down to equal 58.5. So that's how many grams of sodium chloride I would get if all of the sodium reacts with the required amount of chlorine. So we have to have enough chlorine to react with this. Let's see if we have enough chlorine to get to this quantity. And so chlorine's molar mass is 35.45 times 2, which is 70.90. So that's precisely about 1 mole of chlorine. And then for every 1 mole of chlorine that reacts, we get 2 moles of NaCl. Mole of NaCl, 58.45 grams. And so we're going to get a lot more. This would give us 58.45 times 2, 116.9 grams. Would round to 117. Now, this problem here, the second step, like the way I would think through this is if 70.9 grams of chlorine reacts with the required amount of sodium, we would get 117 grams of the product. We can't possibly get that quantity, though, because we would have ran out of sodium when we get to 58.5 grams. So I have enough chlorine to get to 58.5 grams, and I have enough sodium to get to 58.5 grams, but I don't have enough sodium to get past 58.5 grams. So we hit this quantity of our product, and we've run out of sodium. The reaction ends, and we remain with excess chlorine. So chlorine is going to be left over as the excess reactant. Does anybody quickly know how much chlorine gas Cl2 would be left over? Be half of it, right? Because we had a mole of it, and then half of the moles are going to react. So we'd be left with half a mole of chlorine. So we'd be left with about half of that 70.9 gram sample. One of the other problems probably has us calculate the quantity of excess reactant, but you could probably think we could calculate the amount of the remaining reactant. We're consuming half a mole of chlorine. We're consuming a full mole of sodium. So for every mole of sodium, we lose half as many moles of chlorine. So we'd be left with 35.5 grams of Cl2. So hopefully you can see that as a problem. We'll probably see another excess reactant problem later. Okay, so let's look at this problem here. So we have 5 moles of aluminum reacting with excess O2 to yield Al2O3, given by the given reaction, I guess. The reaction would be 4 aluminum plus O2 to form Al2O3. So we're going to have 4 Als plus 3 O2 go to 2 Al2O3 as our balanced reaction. So the idea here would be the number of grams of our product, the Al2O3, that we would form the theoretical yield. We can think of that theoretical yield being the maximum yield we should ever get following the stoichiometry would be all 5 moles of aluminum reacting. Then for every 4 moles of aluminum, we produce 2 moles of Al2O3, and then 1 mole of Al2O3 has a molar mass, that's just our molar mass up here, of 102.0 grams. So 5 times 2 divided by 4 times 102 is 255 grams. So that's the most yield we should get. And if we only get 185 grams, multiply that by 100%. Because I worked this out yesterday, I remember mathematically that would calculate out to be 72.5. So we have particle diagrams, but these questions here are just kind of showing us some collection of molecules that would be present before a reaction takes place, so we can try to quantify or picture what would be present after the reaction. And so here we're showing the N2 plus H2 reaction to form NH3, so it's N2 plus 3H2 to form 2 NH3s. So the idea here would be that we have what looks like 6 H2s, but 3 N2s. And you can think through this problem any way you like. However you get the right answer, it doesn't matter. But you could think through that for every N2, I need 3 H2s. And so for every N2, I need 3 H2s. So I can't react all the nitrogen because I would need 9 hydrogens. But if I react all of the hydrogen, I should be able to react 2 of those N2s with it. You could also picture this. I can take 3 H2s and an N2 and turn those into 2 NH3s. Then I could do it again, take another 3 H2s, another N2, and turn those into 2 NH3s. So I get 2 molecules of NH3. So I should have 4 separate molecules of NH3 that form, and then I should be left behind with an N2. And so that's box 3. So notice here we form 4 NH3 molecules, and we have the N2 that remains. Now, these are wrong here because that's showing like the products aren't stuck together. We don't have 2 NH3s bonded together. 2 NH3 just means NH3 number 1, NH3 number 2 separated from each other, so separate molecules. If those 2 molecules were stuck together, the formula would have been N2H6. So when 2 things are stuck together as a molecule, we change the formula. So that's wrong, of course. This is wrong because we don't have the excess nitrogen, and that's just wrong because, well, the hydrogen count's out of balance. Let's get into some chapter 4 topics. So this question here is asking for a net ionic reaction. Just think of a net ionic reaction be the net reaction. What's the actual change that takes place for this reaction? What we want to cancel out of a net ionic are ions, and the only time we ionize anything is if it's a strong electrolyte. So when I'm looking at my reactants here, H3PO4, is that a strong electrolyte? No, that's a weak acid. That's a weak electrolyte. So when I'm going to write a reaction with H3PO4, I don't dissociate it. When I look at KOH, that's a water-soluble ionic compound, so that is a strong electrolyte. So big thought process is just ionic compounds are either soluble and hence strong electrolytes, or they're insoluble and they're solid precipitates. So this reaction, if I wanted to write the full reaction, it would be H3PO4 plus KOH, and then the base will fully react with all those H pluses to form K3PO4, and that's going to be an AQ because that's water soluble, and then we're going to form water. So we get our salt plus water as our acid plus base products, and then we have 3 H pluses. I'm going to need to get the 3 Ks here as well, so I need 3 KOHs, so I have 3 hydroxide ions to pair up with 3 H pluses. OH minus, H plus, pair up to form a water 3 times. So I get 3 moles of water. And this would be my full molecular reaction. And we call it the full molecular reaction because some of these molecules really aren't molecular in the sense that we wrote them. Like KOH doesn't exist in the solution as KOH. Let me throw some AQ tags in here that we'd have H3PO4 is aqueous. Aqueous doesn't mean water soluble, or doesn't mean strong electrolyte though. H3PO4 is still a weak electrolyte. Sometimes we confuse AQ to be a strong electrolyte. AQ just means it's in the water, it's in the solution. KOH is water soluble, so AQ for it will mean it's K plus and hydroxide ions. So it kind of depends if it's a molecular compound or ionic. H3PO4 is molecular on the weak acid side. KOH is on the ionic water soluble side. Okay, so that's our full molecular. If we want to ionize, we have to keep H3PO4 intact though. So H3PO4 stays intact as that molecule, H3PO4 aqueous. And then the K plus dissociates in the solution into hydroxide ions and K plus ions. Those would be AQs if we want to be thorough and write those AQs in. 3 K pluses in a phosphate ion form because that's a water-soluble ionic compound. And then this is a non-electrolyte. Water doesn't ionize even enough to call it a weak acid, so it's just water liquid. 3 of them. And so our spectator ion is what I'll put in red. There's only one spectator ion here. That's the ion that's in exactly the same form on both sides of this reaction. That's potassium. So we can neglect potassium from the net change. So the net reaction is everything here except the potassium. So it's H3PO4 plus 3 hydroxide ion goes to phosphate plus 3 waters. So it's this reaction here. Now, again, K plus doesn't disappear. It's still there. It's just not part of the net change. I think the idea sometimes it's silly writing these reactions from your guys' perspective of like, why do they want us to write all these silly reactions? Well, it's just really to see if there is a net change. So if you can write a net ionic equation where things didn't all just cancel out, then you know there was some reaction taking place. So I think that's the idea here, is it just helps us understand what the actual reaction was that was taking place. It's a hydroxide ion pulling those H plus ions off of phosphate into the solution to form water. Let's do an oxidation number problem. So calcium, it turns out that's calcium dichromate. You might have worked with it in lab, or you may see it in lab, but it's this formula here. So calcium we know can only be a 2 plus. So that's an oxidation number we have to know by rules, is calcium's a 2 plus based on periodic table placement. Oxygen, also by rule, we have to know it's -2 with a couple exceptions, and the exceptions would be peroxides, superoxides, and if it directly bonded with fluorine. And this isn't one of those exceptions. The peroxide, superoxide, those are cases where oxygen's forming compounds like KO2 or like calcium O2. Again, you know the metal charges based on their periodic table placement. Potassium's always a plus, calcium's always a +2. So here you can infer that oxygen's -1 for the calcium, so that's calcium peroxide. So that's the O2, 2 minus is peroxide. And then this here is -0.5, that's the superoxide, where the oxidation number is -0.5. So you can work out the oxidation numbers of peroxides and superoxides because these are only forming in cases with alkali or alkaline cations. So they're only forming in cases where you know the charge of the metal ion. They're never going to form in any other compound where you don't know the charges. The only other case you see of peroxide is H2O2, where hydrogen by rule is plus. So we get a +2, so that makes an entire -2 for the 2 O's. So you can get the hydrogen peroxide just by the rule of hydrogen and following accordingly to get the -1 for O. When we see Cr2O7, I know that just has to be the ordinary charge. Oxygen's -2 with the exceptions. Let me mention one other exception. If you just have the elemental form of a substance, anything where it's just one single atom, that has to be 0. So if you have F2, that's 0. Sodium solid, that's 0. So anytime you just have the element by itself, then it's uncharged, and it's 0 oxidation state. And so we see oxygen in a compound, it's -2 with the exceptions of the peroxide, superoxide, or compound with F. And so we know that this has to be this type of compound here. The sum of all of our charges of the oxidation numbers have to go to 0. The charge of the overall compound is neutral. And so what does chromium have to be here? +12. So +2 plus 12 is +14. Subtract 14 to get to 0. And so I can deduce that the 2 chromiums have to be a +6 each. So if they're +6 each, gives me a total charge or oxidation number of +12 from the chromiums. And so that gives us a +6 there for chromium. So how do I determine if a reaction is an oxidation-reduction reaction, or if something is oxidized or reduced in the reaction? Well, the only way I can do this is to sort of look at the reactants and products and assign oxidation numbers and hopefully get them right. And so oxidation numbers here, oxygen. Now again, we might be confused, is that a peroxide or superoxide? But just think, is that an alkali or alkaline metal that's bonded to chlorine? So just ordinary O2, -2 for -4. So that's a +4. Chlorine. Chlorine's rule is it's usually -1 except for compounds with O and F. So that kind of fits the suit for chlorine too. Usually we would know chlorine is a -1, but this is one of its exceptions. So water is +1, -2, just by rule for both H and O. The H is +1 in non-metallic compounds. The only time hydrogen's not going to be plus is H2, of course, is 0. But then if you have calcium hydride, calcium's always a 2+, so hydrogen flips to negative. You might recall that one from nomenclature, though. That's calcium hydride with the H- ion. And so hydrogen's always a plus when it pairs up with non-metallic elements. Oxygen's a -2, so I get -6 from the 3 O's, +1. So this chlorine here, I can deduce is a +5. And let me circle this just to imply that I was deducing chlorine's charge from oxygens. And then by rule for HCl, both the H and the Cl should be plus and minus. Okay, so now which atoms undergone a change in this reaction? Did any atoms change oxidation state? Well, the hydrogens were +1 on both sides. Oxygens are -2 on both sides of the reaction. It's actually chlorine that's changing both to be either +5 or changing to be -1. So we have chlorine undergoing two changes. Some of the chlorines are losing an electron to go to +5. And so to go to +5 means we're losing more charge. So we lost an electron. So we lost an electron this way, and they were gaining electrons this way. So chlorine's gaining electrons to go to Cl- from a +4, and then we're losing electrons to go to the +5. So chlorine is actually the atom in this reaction that's undergoing both the oxidation and the reduction. So if we have a redox reaction, we should have both reactions taking place. If something's losing electrons, we have to be able to identify where they're going. So all the electrons being lost by chlorine. If you notice, now this is maybe nothing to get too sidetracked on, but notice how there's 5 chlorines losing 1 electron, and there's 1 chlorine that's gaining 5 electrons. So there is a balance between the electrons being lost and gained here. We're not having electrons disappear or just magically appear. We're just literally changing electrons from one substance to another. Okay. What is the balanced net ionic equation for iron 3 sulfate and KOH mixing? So the reaction that might take place would be a metathesis. Even though I do have KOH as a base, Fe2SO43 doesn't look like an acid. So I'm probably thinking metathesis, an exchange of the ions, and does something become insoluble? So if I'm writing Fe2SO43, presumably this is aqueous, right? Because that's not one of the insoluble exceptions for sulfate. So sulfates are generally soluble with 4 exceptions. You can consult the solubility chart if you need to. That's available on the test. If you go to the practice exam module, there's a little link that has the practice exam packet for midterm 2. You'll see the second page has a solubility chart. So we hopefully know that's water soluble. Potassium hydroxide, of course, is water soluble. But what would be insoluble here would be iron hydroxide. So we keep iron 3+. So iron 3+ with hydroxide ion. So we have FeOH3. This is going to be the insoluble precipitate. And then if I'm writing the full molecular reaction, I'd write K2SO4. That's water soluble. If I want to balance this whole reaction, I would probably try to balance the sulfates first. So 3 sulfates on both sides. So that gives me 3 sulfates on both sides. I need 6 to give me the 6 potassium ions. And then 2 FeOH3s. So that gives me 6 hydroxide groups on both sides. So that looks to be in balance. Now, if I want to write the net ionic equation, I just have to ionize the things I can ionize, the strong electrolytes. So I can write this as 2Fe3 plus SO42 minus 3 of them, and then plus 6K plus 6 hydroxide ions. And these are going to form FeOH3, 2 of them. Solid, so I can't break apart the solid into its ions because they're not in the solution. So this thing here remains intact. That's not a strong electrolyte, of course, because it's the insoluble precipitate. And then I can break apart the 6K plus in the 3 SO42 minus ions. So SO42 minus is one of the ions that's the same on both sides. I neglected all the AQs. I could have written AQ like a bunch of times here. But all the ions are, of course, AQs. So the sulfate would cancel, and then the potassium ion would cancel. And so the net ionic equation should be the iron and hydroxide combining to form FeOH3. And the only slight little detail is you could cancel out, because if you look at the reaction as is, it's 2 plus 6 goes to 2. So we can just cut those in half and go to 1 Fe3 plus 3 OH minuses form FeOH3 and simplify down that net ionic equation. So net ionics, to me, sometimes they seem strange. It's really just asking the question or trying to get at, is there actually a net change taking place in this reaction? And there is. The net change is the formation of that ionic compound that's insoluble, iron 3 hydroxide. Let's look at the next problem. That's not this button. So the next problem talks about adding lithium chloride to 250 milliliters of flask and filling to that 250 milliliter mark with water. And so then we can calculate the concentration of lithium chloride. So it looks like we make a lithium chloride solution, and then we're going to take some of that solution and dilute it. So we're going to make a solution, calculate its concentration, then we're going to try to understand its dilution. So let's do this problem in a couple steps. So my first process is I take the moles of lithium chloride that initially I put into this flask, and I initially fill it to 0.250 liters, because molarity, we usually think moles per liter. And so I go moles per liter. That works out to be, what was that, 0.6? So that's 0.60 molar lithium chloride. Now, in a lot of problems, you're going to be better served to not necessarily write the capital M, but to just distinctly write moles of lithium chloride per liter of solution. So you can think M, that's fine, but just remember it's moles per liter. Moles of lithium chloride per liter of that solution. So then we took a pipette and took 4 milliliters of this solution, 4.0 milliliters of that solution, and then added it to a new 50 ml volumetric flask. Now, a volumetric flask is just a flask calibrated to hold 50 milliliters fairly precisely. Okay, so the idea is you have a flask that you can fill to a line. It's kind of like a burette, but easier to use. So it's like something that can contain a certain volume. So we take 4 milliliters of this solution, and then we fill it to the top with water for the remaining volume. So the new concentration of my lithium chloride, once I dilute it, I can think of this a couple different ways. Why don't I think of it the most simple way, which is, well, let me just take the 4 milliliters, which is 0.0040 liters, and just multiply that by the concentration of the solution, which is 0.60 moles lithium chloride per liter of that solution. So that's the number of moles I transferred to my new flask. And then why don't I just divide this by the volume of that new solution? So I take 0.04, or 0.004, so 4 milliliters converted to liters times 0.6 moles per liter. That gives me 0.00 moles of lithium chloride. So I take that number of moles of lithium chloride and I divide it by 0.05 liters. And I divide by 0.05, I get 0.048 moles of lithium chloride per liter of that solution. And that's capital M. For answer B. Now, we could have equivalently set up an MIVI equals MFVF. If you ask me, anytime you have to go to an equation, you might want to ask yourself, do you really understand the equation? Do you understand where it comes from, how it's used, the proper problems to use it in, or is there just some simple concept we can use instead? If you can just use the concept of molarity is just mole solute by volume solution, I think you can get every question correct. If you want to rely on the equation you might forget or not know how to use or misapply to a problem that it doesn't apply to, I would take some caution there. So you can use MIVI equals MFVF very easily because you're just taking the 0.6 molarity times 4 mils dividing by 50. So that works too. So it's not that that's wrong. It's just making sure we know the equations and topics that we're doing problems with. So questions 11 and 12 get at stoichiometry type problems from chapter 4. And so the first one says we have HCl. And so we have 0.189 molar HCl. How much of it is needed to fully neutralize, that means just fully react with, 2.87 grams of calcium hydroxide with a given molecular weight according to the below reaction. So I have 2 HCl moles have to react with 1 mole of calcium hydroxide. We know the products, the salt plus water, calcium chloride plus 2 waters. And so hopefully I can solve a stoichiometry problem here. How many milliliters, what volume in milliliters of this solution is needed to fully react with 2.87 grams of calcium chloride? When we use the molar mass here, it's 74.10 grams per mole of calcium chloride. For every one, oh, I'm saying chloride, it should be calcium hydroxide. So 2.87 grams of calcium hydroxide. I use the molar mass of calcium hydroxide to go to moles of calcium hydroxide. According to my balanced reaction, for every 1 mole of calcium hydroxide, we have to add 2 moles of HCl to fully neutralize it. Sometimes the word neutralize confuses people. That just means to completely react with. How much HCl is required to completely react with this given quantity of calcium hydroxide? So we're just using the coefficients in our reaction, and then we can divide by the molarity. Why do I divide by the molarity? Well, let me write it out. It's 0.189 moles of HCl per liter of that solution. And we want the milliliters of that solution, so let's just do one more step. Let's multiply this by 1 liter of solution is 1,000 milliliters. So 2.87 divided by 74.1, that's just the moles of calcium hydroxide present. For every 1 mole, I need 2 moles of HCl, so times 2. And I'm delivering it in 0.819 moles per liter, so divide by 0.819. And then times 1,000 to go to milliliters. So I get 94.6 milliliters. Now, if you ask me, the only time I usually see students miss this question is when they don't write anything out, or when they try to do all the math in their head, and they miss the units, or they're not writing out distinctly the moles of HCl per liter of that solution. If we just forget what M means, and we're just, maybe then we're multiplying by molarity instead of here where we would need to divide by it. So if you find that, if you say to yourself on a practice test, oh, I multiplied by the thing I needed to divide by, well, why? Probably because we didn't show the units, or we didn't write out the work. If you can get these problems right, like I could get this right without showing the work. I mean, if you can write the problem out and get it right and you're doing this on practice exams, yeah, you can probably skip the work. But if you're getting the answer wrong and skipping the work, just write the work out. It's not that hard, it doesn't take too much longer. It'll save you the time from recalculating things anyways. Okay, so let's also talk about question 12, which is a titration type problem. So here we have the question, what is the molarity of a solution where we have 20 mils of the solution of H3PO4 that requires a certain volume of KOH to fully react with it. The idea of a titration problem is a titration is sort of ran with the idea that you have an acid and I can add base to it. The moment I add 3 moles of KOH for every mole of H3PO4, I see a color change. Titrations are designed that there's some kind of design or some kind of indicator that's going to go off and change color, or something's going to be indicated to us that we mark that perfect stoichiometry point so that we can dropwise add one to the other and figure out the precise volume to exactly neutralize the solution. And we often do this to determine unknown concentrations. And so imagine you have 25 gallons of phosphoric acid. You want to know the concentration of it. You take a small portion, test it here in a titration. And so what we're trying to determine is the concentration of the H3PO4. And we're trying to determine that concentration before we even begin the titration. So how many moles of this were initially present in the reaction? So that would be the moles of H3PO4 that are initially present. Divided by the volume of that solution. And I know the volume of the solution is 20 milliliters. So I already know that volume. So what I need to determine using stoichiometry is how many moles of H3PO4 are present in the solution. So that's what I need to plug in is the moles of H3PO4. So why don't I try to solve for it using stoichiometry? Let me also mention here, you see the word molarity, you see a volume, you see a molarity. Is anybody in their head going M1V1 equals M2V2? You can raise your hand if you think you're thinking M1V1 equals M2V2. Don't think M1V2 equals M2V2 here. It's not going to work. We have to solve the stoichiometry problem. So this is what I was meaning, where sometimes you see an equation, you think it could be applied here. It's not applied here. This isn't a dilution problem. And so I'm going to take the volume of my solution of KOH, but in liters, so 0.0535 liters. I'm going to multiply this by 0.248 moles of KOH per liter of that solution. And then for every 3 moles of KOH means that I added, means that 1 mole of H3PO4 had to be initially present. So for each mole of H3PO4 that's initially there, I have to add 3 moles of KOH. 0.0535 times 0.248. What the M1V2 over the MIVI equals MFVF is missing that 3. That's why we need to do the stoichiometry problem. So we need to divide by 3. So I'm going to plug this result in up here. It's 0.00442. I'm just taking that number of moles, dividing by 0.02, and I get 0.221 molar. Now, again, why do I divide by 20 mils or 0.020 liters? It's because I want to know the H3PO4 concentration in that solution that was initially present. So sometimes I see students dividing by the sum of the 2 volumes or saying, how do I know when to add the 2 volumes up? And it's like, well, we just have to take the context of the problem into account. We want to know how many moles of H3PO4 were initially present to add to this quantity, by how much KOH had to be added to the quantity to fully react with it. So we just solve for the H3PO4 initially present. Sometimes I find there's some confusion on initially present versus reacted. You know, like, this is a problem where if you actually set up a BCA chart, it should make sense because you can imagine there's some amount of H3PO4 initially present. You don't know how much KOH you have to add, but if you think of the minus X versus the minus 3X, once you see that both the KOH and the H3PO4 are going to 0, the idea is to try to find out how much KOH you had to add to lose 3X of it to go to 0. You solve for X. X is the amount of the H3PO4 initially there. If I lost you, maybe I did, I don't know, I'm going fast, I understand, but the BCA chart shouldn't be necessarily the way we go to solve a problem, but it should help us understand it. If we're getting lost on initially present versus reacted versus what went to 0, set up a few BCA charts and just try to really understand them, because they're what I'm really thinking, what's initially there reacts to 0, how much KOH did I have to add, it reacted, it went to 0 too. Both of these things, if you think of this reaction where you have some initial concentrations of whatever they are, after the reaction they're both 0. Like, that's the idea of a titration, is you're hitting the magic point where you had just the amount of the one reactant to fully react with the other. So that's what a titration is meant to do, is to mark that point for us so we can see that with our eyes. Okay, so I'm not going to have too much time to get into chapter 5 problems, but I probably have a minute or two to get through a couple of these. And so we have an internal combustion engine burning gasoline to accelerate a car. So the car is accelerating. And so what is the sign of Q and W for that combustion reaction occurring in the car? So combustion reaction goes with the flame. That's heat being given off by the reaction. So we know that the reaction, that's a terrible Q, the reaction is losing heat. Because the heat is being lost to the flame, it's heating up the engine block. So heat's definitely being lost by this reaction. Definitely an exothermic reaction is taking place. And then we're putting a car into motion. So if we're moving the car, that's the reaction doing the work on the surroundings. The car is the surroundings. It's working on the surroundings, so the work is also negative. I like to think of this example here because it shows me how the sign of Q relates to W. If I can heat something up, my Q is negative. If I can move something, my W is negative. relative to me being the chemical reaction. So reaction gives heat off, gives off energy to put things into motion, that's W negative. And so Q and W should both be negative here. Answer A. If we have a piston in two, so we have gases in a piston. I really like this question. I don't know when I wrote this. But you have two gases that are in like a gas cell, then they react together, and the cell ends up contracting as that reaction takes place. But then we have like a water bath surrounding that container where the reaction is taking place, and that water temperature goes up. So the water temperature goes up surrounding this reaction. So the temperature of my surroundings goes up here because the reaction had to lose heat. But then the contraction was coming inward. It was the surroundings working on this reaction. So the W here was positive. So I tried to think, what's an example of W positive? It's just a case where the motion's coming inward towards the reaction, not outward. So this is the surroundings working on the system. So the W for the reaction is positive. It released heat, so the Q is still negative. So Q negative, positive W. And then I'll end with this one, delta E is Q plus W. So if Q here is negative, W is positive, we have no idea what the sign of delta E is. So delta E is the sum of the two. If they're both negative, delta E is negative. They're both positive, delta E is positive. One's positive, one's negative. We don't know. We need to know the actual numbers. So we don't know and can't interpret the sign of delta E from this information. So these problems are just from daily quizzes. So if you want to know some of these solutions, just go to the daily quizzes. I have the key for this up too. A lot of daily quizzes have video solutions. So check those out if you're looking for problems to work on over the weekend. If you have questions, feel free to email me. I'll respond to emails if you email me questions. Office hours today till 12:30 and 2047, 2 to 3s are canceled. So, all right, guys, have a great weekend.